My name is Enda Carroll. I am the current president of the SIAM-IMA Dublin Area Student Chapter. I'm in my second year of my PhD in Applied Mathematics at University College Dublin. My research focuses on studying the dynamics of the so-called Fourier phases in nonlinear systems that describe the motion of a turbulent fluid. My research would lie in the area of fluid mechanics, or more specifically in the field of turbulence theory, where the overarching goal is to come up with a model or a theory that would allow us to describe the motion of a turbulent fluid. Turbulence is such a widespread and universal phenomena that we witness its effects every day. Turbulence shows up in any system that has a moving fluid. For example, in the airflow in your lungs, or the swirling of milk in your morning cup of coffee. Turbulence can even be seen at the scale of planets, where the motion of ocean currents, the formation of clouds, even the weather are strongly influenced by turbulence. You can even see turbulence in the churning storms in the atmosphere in Jupiter. A true understanding of turbulence would have a huge positive impact on society. It would allow us to predict catastrophic weather events like hurricanes and storms, produce more efficient wind farms, and design more fuel-efficient aircraft. One of the defining features of turbulence is that it consists of many swirling vortices, or eddies, at various scales and sizes. These vortices contain most of the energy in the fluid, and this energy is exchanged from large scales down to small scales, where the energy is dissipated away at the smallest scales due to viscosity. What makes turbulence such a difficult problem is that the interaction between these large-scale and small-scale events happens in a nonlinear fashion, which produces chaotic and often unpredictable motion. The model or equation we use when referring to turbulence is known as the Navier-Stokes equations. These equations are used to describe the motion of a fluid. They encapsulate effects a typical fluid would exhibit in a given flow, namely its density, the fluid's acceleration and convection, the internal forces such as pressure and viscosity, as well as external forces like gravity. There are two schools of thought when it comes to tackling the problem of turbulence. The first approach is from a statistical standpoint, where instead of predicting the exact position or velocity of a fluid, which is impossible given its chaotic nature, we ask questions like, what's the average velocity in a given region? Or what's the distribution of energy at small scales? This statistical theory is the prevailing theory in turbulence and is known as K41 Theory after a Russian mathematician, Kolmogorov, who pioneered it in 1941. The second approach, which has been developed more recently, is from the point of view of dynamical systems, where we think of turbulence as being this chaotic attractor in the phase space of the flow of the fluid. Both approaches have been useful and have helped us understand some important facts about turbulence, but they're not complete. There are still some open problems in the theory of turbulence. One of the open problems that my research focuses on is the problem of intermittency. Intermittency refers to bursts of energy dissipation in turbulent flow. In physical terms, essentially one sees sporadic or intermittent events of intense turbulence. These extreme events have been discovered in experiments and numerical simulation, but they come into conflict with the prevailing statistical theory, K41 theory. As a mathematician or a physicist, when we refer to intermittency, we usually mean non-Gaussian statistics. What this means is that if you were to look at the statistics of the velocity of a turbulent fluid, you would see these large fluctuations being far more probable than what you might expect. And this is what we mean when we refer to intermittency. As I said, intermittency is still an open problem in turbulence theory, and we still do not know exactly how and what causes these large bursts of energy. And this is where my research comes in. My research focuses on using the so-called Fourier phases as a tool to try and understand this mechanism that gives rise to intermittency in turbulence. The Fourier phases are simply dynamical variables that you get when you take a Fourier transform of the equations of motion, like the Navier-Stokes equations. My research to date has involved studying the dynamics of these Fourier phases in a time model for turbulence known as Berger's equation. We've been able to show that they are extremely important when it comes to describing turbulent phenomena in this model. They act as bridges that transfer energy from the large scales down to the small scales. Going forward, we are looking at using these Fourier phases as a tool to link both approaches to tackling turbulence. And as well as that, take what we have learned in this small toy model and apply it to other turbulent models such as the Navier-Stokes equations. Hopefully, I have given you a brief overview of what turbulence is, some of the open problems in turbulence, and a flavour of the research I do and the research we do at UCD. Thanks for listening.